right, so on that note, we're going to talk about gravitational fields. We talked a little bit about this yesterday, okay, but we want to go into a bit more detail today, okay? So gravity is a field force, just like electricity, just like magnetism, okay? It can exert a force without being in physical contact with the other object, okay? Friction is a contact force, okay? There's no friction if there's no two objects in contact with each other, okay? Even if that's something moving through the air, it's in contact with the air, it's a contact force, okay? So gravitational field strength, as we said yesterday, is numerically equal to, or is a different way of saying, gravitational acceleration, or acceleration due to gravity. So on that note, okay, I want you guys to write down what I'm going to put on the board because this isn't in the notes. The most common source of confusion to do with gravitational attractive force and gravitational field strength is terminology. Okay, so if I see this, okay, I'm talking about the force of gravity. And we name that force in a few different ways. Okay, sometimes we call it the gravitational attractive force. Okay, sometimes we call it force of gravity. Okay, or sometimes we call it force of gravitational attraction. So it's just a restatement of the top one, but okay, and lastly, we also sometimes call it weight. Okay, so in all of those terms, with the exception of the last one, the word force is in there. Okay? When I'm asking a question where I want you to calculate the force of gravity, okay, I will use either the words force of gravity or gravitational attractive force or the force of gravitational attraction. I will use the word force. Okay? If you see the word force, then you're looking for Fg. Okay? Now, the thing we're talking about today is this, little g. Okay, little g, we've called up to this point, okay, acceleration due to gravity. Okay, we also sometimes call it gravitational acceleration. And, as we're going to learn today, gravitational field strength. Never looks right. I hate that rule. I before E except after C, except in most of the words that actually have I and E in them, right? English is a silly language. Okay, so those would be the terms I would use if I was asking you to calculate for me the little g. Okay, I would either say acceleration due to gravity, gravitational acceleration, or gravitational field strength. Notice that in none of those names is the word force. Okay, because what happens most often when I give a question where I'm looking for something about gravitational field strength, I get people solving for the force of gravity. They are not the same thing. Okay, so that's why I'm putting that down there, and I want you to have a look at that so you know those are the different ways I can name little g and Fg. Okay, they are different, okay, and they are calculated differently. Okay. All right, now, we said yesterday that the formula we're going to look at today is actually derived by putting the force of gravity equal to itself using the two different ways to calculate force of gravity. Okay? if we know what little g is, we can go m times g and we'll get it. Okay? If we don't know what little g is, but we know the two masses and how far apart they are, then we can use big Fg. Okay? Newton's universal law of gravitation. Since those calculate the same thing, okay, I can definitely write that they are equal to each other. And when I do that, one of these masses cancels. Which one? The big one or the small one? The small one. Okay? We talked about this yesterday, but that's because any mass caught in another mass's gravitational field will have the same acceleration due to gravity regardless of their mass, or the way we said it in Unit 2, all things fall at the same rate. Okay? Mass does not affect the acceleration due to gravity. It applies to all masses. The same is true for gravitational field strength because they're the same thing. Okay? So, basically what we're looking at here is that mass will cancel, okay, and we're going to have little g equals big G times the big mass divided by how far apart the two masses are. Okay? Now, if I gave you a question that was about this formula, what are some ways I could try to throw you off track? Because that formula is a lot like the bank curve formula. It's only used to do one thing. It's never set equal to anything else. It's just for doing gravitational field strength. So if I wanted you to calculate gravitational field strength, I would have to give you the mass of the object generating the field and how far the other object is from its center. Agreed? Could I give you other things to try to throw you off? Like what? What would be the easiest thing to give you that you don't need?
Mass of the satellite?
Yeah, I can give you the mass of the object caught in the field. Okay? Would that make it seem like you would want to use the other formula because you have two masses? Absolutely. Okay? This is why I'm bringing this up. Okay? I want you to know that if you see these words, you're looking for little g, and the second mass isn't part of it. Okay? There's only so many ways, okay, that a gravitational field strength question can go. Okay? I'm either going to give you the field strength and ask you for R, give you the field strength and ask you for M, or give you M and R and ask you for the gravitational field strength. Okay? This is not a hugely difficult concept or formula to use. Okay, so Newton and actually Faraday, okay, were two people who did a lot of work with field forces. Coulomb kind of came along and mathematically made the idea work. Okay, but the idea of the field was known or theorized quite early on because it made it possible to not have to talk about invisible magic ropes and strings and things like that that connected objects to exert the forces. Okay? Before the idea of the field, okay, people imagined that the Earth and the Moon were connected by an invisible rope that held the Moon in orbit. Okay, like there's always, an invisible fluid or an invisible rope or whatever these things. It was all magic. Okay, well, the field force kind of eliminated the need for that, especially since that's obviously not true. Okay, so the idea of a field, okay, kind of excused that idea and made it possible to explain why the Moon, for example, would stay in orbit around the Earth. Okay, it's caught in the Earth's gravitational field. Now, does the Moon have a gravitational field? Sure it does. You have a gravitational field. It's puny. Okay, but you have one, right? The bigger the mass is, the greater the gravitational field that it can exert. Okay, of course, the strength of that decreases exponentially as you get further away. Okay, but the Moon clearly has a gravitational field because we see and feel the effects of that on Earth. Okay? Where's the main place where we can observe the effects of the Moon's gravitational field?
The ocean?
Yeah, it's the tides, absolutely. Okay, the tides happen because the fluid ocean is pulled towards the Moon. Okay, so as the Earth spins under the Moon, okay, the ocean is always attracted to the Moon, which is why you get high and low tides. As the Earth spins underneath it, a different part of the ocean is pulled that direction. Okay, And obviously tides are not perfectly consistent, right? Sometimes you get, abnormally low tides, and sometimes you get abnormally high tides, okay? That has to do with the fact that the moon's orbit isn't perfectly circular, okay? Sometimes it's closer to the Earth than others. Its gravitational effect is amplified by that, okay? And so we get higher or lower tides, okay? Everybody all right with that? Okay, so this was Faraday, okay, and his field idea, okay? It really helped to explain all of this kind of stuff here, okay? So a field acts on another body at a location, okay, a given separation distance. So that idea of R is still the center to center separation distance. That part doesn't change, okay? All right, so if we were to look at the gravitational field of a isolated object, this is what it would look like if we diagrammed the field strength as arrows, okay? The field always points towards the center of that mass, but the further away you get, the weaker the field becomes, okay? And that's what we're seeing here, right? Now, very rarely do you have a mass that's in isolation, okay? Even if you looked at something like just the Earth and the Moon together, okay? Would the Earth and the Moon cause changes in some of these arrows? Right? Once you slap the moon in there, okay, the moon's gravitational field is going to alter the direction and the length of some of these arrows as the fields overlap. Okay, so it would look kind of something like this. Okay, so this would be the Earth, and this would be the moon out here. All right, so on the far side of the Earth, the moon's gravitational field doesn't really do very much. Okay, but on this side of the Earth, we can see that, okay, now you've got to do vector addition basically with those arrows to see what the resulting force would be. So sending somebody to the moon is not as simple as just, okay, the moon's going to be over there in 3 days when they get there, so point the ship over there. Okay, it's not that simple. Right? As you get closer to the moon's gravitational field will start to affect your trajectory. Okay? You'll have to correct for that. Right? If you want to fall into orbit around the moon, which they usually do, okay, you've got to slow yourself down so the gravitational acceleration is sufficient that you maintain an orbit. Right? You're falling all the time, but you never get any closer. Okay? All of that is fairly complex calculating that's got to go on. Right? Now, right here is a point of gravitational balance. Okay? The gravitational field strength of the moon and the gravitational field strength of the Earth completely cancel each other. Okay? What would you feel right there? Like nobody's attracted to you at all. Okay? Right there, you would have no net gravitational attractive force in either direction. Okay? That's how you would feel at that point. Okay? We actually call those Lagrange points, if anyone's ever heard of that term. Okay? Lagrange points happen all over the solar system. They are points of net zero gravitational field strength. Okay? If you could put an object at that position, it would require zero maintenance. It would just stay there. Okay? Because it would always be in a point of net zero gravity. Okay, so similar idea here, okay? As you get further away, obviously the lines get shorter because that's an exponential relationship. All right, so if we're looking at kind of different, okay, gravitational kind of forces, obviously the smaller the mass, okay, is going to reduce the gravitational field strength. But remember that radius also has an effect on that, okay? The moon is considerably smaller, mass-wise, than the Earth, but it's also considerably smaller radius-wise than the Earth, okay? And so that makes a bit of a difference in terms of how heavy you would feel there, okay? Because obviously if you're standing on the surface of the moon, you're quite a bit closer to its center than when you're standing on the surface of the Earth. All right. All right, I would like you guys, I'm going to blow that up a little bit, make it a little bit bigger, but I want you guys to try, let's say 2 and 3. Okay, so I'll give you a couple minutes there on 2 and 3. The answers are right here if you want to check. All right, so for number 2 here, okay, we have an 80 kilogram astronaut, okay, in orbit, and they are 3.20 times 10 to the 4 kilometers from the Earth's center. What do I need that in? Meters. Okay, so that's 3.20 times 10 to the 7 meters, right? 1,000 times more, 10 to the 3. Okay, so I know that R is going to be 3.20 times 10 to the 7 meters from the Earth's center. Okay, use the data from table. Well, okay, the data from that table is basically this: the mass of the Earth and the radius of the Earth, which are numbers that are on your formula sheet. Okay, so calculate the magnitude of the gravitational field strength at the location of the astronaut. Okay, so little g equals big G times which mass? Astronaut or Earth? Earth. Earth is generating the field. I mean, the astronaut's generating a gravitational field too, but it ain't doing nothing. Okay, it's just too small. The Earth's gravitational field is huge. All right, so G times the mass of the Earth over the radius, which they gave me, squared. All right, all I have to do is plug in my numbers. 6.67, I already have it open, okay, times 10 to the minus 11 times 5.98 times 10 to the 24, okay, divided by 3.20 times 10 to the 7 squared. All right, and if I punch all of that in, which we will here, okay, so 6.67 e negative 11, 5.98 e 24, okay, 3.2 e 7 squared. Okay, I mess up a number there. Okay, so 0.389, what did I get? I got 0.38, I got 0.400 actually. Okay, but that's the small differences between their table and our values on our worksheet. Okay, and that is newtons per kilogram, or what's the other way I can write newtons per kilogram? Okay. We talked just briefly about this yesterday. Normally, what are the units for G? Meters per second squared. It's gravitational acceleration. Okay? When we talk gravitational field strength, we usually write it newtons per kilogram. What are the fundamental units of a newton? What do I multiply together? Mass and acceleration. Okay, so a kilogram meter per second squared divided by a kilogram leaves me with meters per second squared. Okay, so newtons per kilogram and meters per second squared are exactly the same thing. Okay? All right, what would the magnitude of the gravitational field strength be if the astronaut was orbiting the moon with the same separation distance?
What is it 10 to the 7?
Because I need it in meters.
Oh.
It was given to me in kilometers, so I just converted, made it 1,000 times bigger, 10 to the 3. Yeah? Okay, so if this was the moon instead, here's all I do. I go second entry, and I change the mass of the Earth to the mass of the moon instead. Whoop, too far. Okay, so I go 7.36, and then I put in 22 instead of 24, and I hit enter, and there it is on the moon, or for the moon. It's a lot smaller, because the moon is a lot smaller. Okay, everybody all right with that? How many people have done number 3? Okay, I'll give you a few more minutes on number 3, and then we'll talk that one over. Little g or FG? FG. What's the word in the question that tells you that? Force. Okay, force is in this question. Exactly why I wanted to go over this one. Okay, it's easy to fall into a pattern, okay, and then not read the question carefully. Okay, in this one here it says the highest satellites in orbit the Earth at this distance. Lovely, wonderful. Okay, from the Earth's center. What would be the gravitational force on a 70 kilogram mass? Okay, well, then we got to do this. Big G times the mass of the Earth times the mass of the astronaut, okay, over R squared. Okay, and so that for us is going to be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 70 kilograms, okay, divided by 6.6 times 6.37 times 10 to the 6 squared. Okay, 6.6 times the Earth's radius. All right, so when we punch all that in, okay, we'll have 6.67 e negative 11. Whoop, not 14, 11. Okay, 5.98 e 24. Right, and then 70. Okay, that looks like 16 newtons to me. All right, so really be careful, really read the questions carefully, especially next Thursday, okay, on your unit exam. That is exactly the kind of trap that people can fall into. It's just, oh man, because I mean, when it comes right down to it, do you have to do much for that question? You don't even have to do any algebra, right? You're just plugging numbers in. But if you plug them into the wrong formula, then you're going to get nothing, except your Gibbons mark. Okay, so obviously we don't want that to happen. Okay, make sure you're looking, does it say gravitational field strength? Does it say force of gravity? All right, what was the other one I wanted you to do here? Oh, question A. I always like this one. It's like a good multiple choice kind of question. What's the mass of a 60 kilogram student on Mars and then on Earth? If you're looking at this and smiling and going, I think I know the answer and it seems really dumb. You're right. What's the mass in either place? 60 kilograms. Your mass is how much of you there is. Okay? This is a question that tests, do I understand the difference between my mass and my weight? Something pretty important from this unit. Okay? And that's easily a multiple choice kind of question, and I would snag people with it. Okay? Because you get going, you're a little anxious, don't read the question quite thoroughly enough, okay? And you get caught on one like that. Okay? Now, what's the student's weight? Well, that would require us to do a force of gravity calculation because weight is force, not field strength. Okay? Just those little things, okay? The importance of reading the question really carefully. Okay. Okay. I want you to try this one here, and then we'll start our unit exam review, okay? Just a gravitational field strength question. So, on this one, they're looking for the distance from the Earth's surface. That's the trick on this question, okay, is it wants it from the surface. Our formula calculates R, not from the surface, from the center. Okay, so we'll have to do one extra little calculation here at the very end. They also tell us G, okay, 7.33 newtons per kilogram, and they tell us that we're dealing with Earth. So we would use the mass of the Earth as a given here as well. Okay, so they said gravitational field strength, so just like the bank curves, I only use this formula for one thing. Okay, so I write it down. That's the gravitational field strength formula. Now I'm just manipulating it for R. Okay, so R will be the square root of big G times the mass of the Earth over little g. Okay, plug in my numbers here. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 7.33, all square rooted. Okay, so that is the center to center distance. I only want the distance from the surface, so I'm going to subtract 6.37 times 10 to the 6. There's my distance from the surface, 1.01 times 10 to the 6 meters. Okay, that's a pretty common thing for a field strength or satellite question to do. Okay, to ask you what the altitude is or what the height is. Okay, or conversely give that to you and know that you would have to add the radius of the Earth onto that number. Okay. Questions? Okay. Let's have a look at our unit exam review here, guys. Okay, so obviously a week from today, okay, is our unit exam for this unit. We'll be done this unit, well, me teaching you new stuff today. We're actually already done that. Okay, I just taught you gravitational field strength, that's the last thing. All right, on Monday, you'll work on an assignment on gravitation and have the whole class to do. Okay, and then we'll start unit 4. So, first thing we talked about in this unit was like period and frequency, okay, and V equals 2 pi r over t. Okay, so uniform circular motion, okay, meaning that we have a constant speed but a changing velocity. Okay, if the velocity is changing, then there's a centripetal acceleration. Okay, that's the kind of stuff that would get tested in a multiple choice question. Okay, the understanding of the principles of circular motion. If something's going to move in a circle, there's got to be a force pulling it in. Okay, it's going to accelerate in. Its speed will be constant, but its velocity will change. Okay, and so we also talked quickly in uniform circular motion about centripetal acceleration, okay, v squared over r, as well as centripetal force, mv squared over r, okay, being mass times acceleration. It was Newton's second law applied to a circle. Okay, your centripetal force is your vector sum of all forces. Okay, then we talked about the different examples of things moving with uniform circular motion. We talked about something on a string being whirled around and around, and then we went into the 2 types of curves. Okay, we talked about unbanked curves, and we talked about banked curves. Expect problems to do with those, either a numerical response or a written response question on those 2 things on the unit exam, 1 of each. Okay, what keeps you in an unbanked corner? Friction. Okay, if you're going around a flat corner, okay, that isn't tilted, it is friction that keeps you from sliding. Okay, so something that we have to remember there, because actually I saw that as a pretty common mistake on the last quiz. Okay, I saw a lot of people for unbanked corners go FC equals FG. Gravity is perpendicular to this. Okay, it doesn't have any effect on that. Okay, it's in an unbanked corner. Okay, force of friction acts as a centripetal force. That's mu times mg, yes, but mu has to be part of that. It is the friction that holds you in the corner. Okay? All right, so that comes down here to unbanked curves. Okay, that thing we just talked about. Okay, mu mg equals mv squared over r. Okay, for a banked curve, so now the ground is tilted, okay, what keeps you in that corner? Normal force, okay, or at least the horizontal component of it, okay, because if you've got a tilted surface, as you're going around it, gravity pulls you into it and it pushes back perpendicular to the corner, okay, but also your own inertia causes you to push on that surface, okay, because you want to leave the circle, so you push even harder, okay, meaning that there's even more normal force, okay, that's holding you in it, in the corner, right? So that's what this diagram over here is talking about, okay? We've got basically an inclined plane, gravity pulls down, but the surface of the corner can only push perpendicular, but you've also got your inertia pushing on it, so normal force becomes the hypotenuse, okay, and the horizontal component here is the centripetal force, okay? As long as you understand that, you're good. You don't ever have to derive the bank curve formula. It's on your formula sheet, it's on the front of the exam, okay? So you won't have to derive it, but it is important to understand how the curve works, okay, for a multiple choice question. Okay, nice thing about bank curves, we know that there's only one formula that governs how they work, and we just have to know if that's the one to use, okay? And those questions then become pretty easy. Okay, after banked curves, we talked about artificial gravity. Okay, oh, sorry, I gotta go further down here. Right, so tan of theta equals v squared over rg, that's the bank curve formula. Okay, then we talked about artificial gravity. Okay. In artificial gravity, you're standing on the inside of a spinning cylinder. Okay. Your inertia wants you to go in a straight line. That causes you to push on the inside of the cylinder, which of course has a reactive force that pushes back towards the center and feels like gravity. Okay. So that's why artificial gravity questions usually come down to this. Okay? Unless they say something like you would feel half of your Earth weight, okay? Then you would say, all right, mv squared over r equals 0.5 mg, okay? It's still going to be mg. It's going to feel like whatever factor of gravity they tell you. All right, so those are pretty straightforward as well, okay? Just, you know, if you get an artificial gravity question, Fc equals Fg, or whatever factor of Fg they indicate. All right, so that was all the uniform circular motion stuff, where the speed is constant, okay? Then we went to vertical circular motion. Okay, sorry, this was my diagram for the artificial gravity question. So your inertia wants you to go in a straight line, okay? That would be this line here, okay? Because you want to do that, the cylinder pushes back, and then you feel like you have weight, even though you really don't. Yeah. Okay, that's not real gravity, okay? It's not real weight. It is, what's the other name for normal force? Something weight? Apparent weight. Okay? All right, then we talked about vertical circular motion. The key thing with vertical circular motion, it's the vector sum of all forces. Forces in minus forces out. Okay, you will definitely get at least one vertical circular motion question. Your first step is to draw it out like a free body diagram so that you can identify what forces are acting, are they in, are they out, set up the form. Okay, so we talked about the different situations here. We talked about if you're going over the top of a vertical circle, okay, that gravity is then acting in and normal force is acting out. Unless you go fast enough and normal force becomes zero. Then you would be apparently weightless, right? Okay, that's that zero gravity trainer thing that we watched the video of. Okay, if you are going under the top of a vertical circle, that is where minimum speed may come into play. Okay, so there's only a minimum speed for the top on the inside because that's the only place you can actually fall. Right? So if you see a question that mentions the word minimum speed, you know you're dealing with this situation. Okay? The other thing to remember is that if you are only going the minimum speed, you will feel how will you feel? If you're going just fast enough to stay in the circle, will you push on the circle? Will it push back? How will you feel? John, how will you feel? You will feel apparently weightless. Okay, so you can produce a feeling of apparent weightlessness both on the inside at the top and on the outside on the top. But you can never make that situation happen if you are on the bottom. Okay? On the bottom, you are always going to feel apparently heavier than normal. Okay? Because on the bottom, okay, gravity wants to pull you out of the circle, your inertia wants you to go straight, you push really hard on the track, and the track has to push really hard in response. You will always feel either normal, that means you're not moving by the way, or heavier, okay, if you're in motion at all. Okay, we did have some questions that we did in class where it said you feel 3 times heavier than normal. Okay, if you feel 3 times heavier than normal, then your apparent weight is 3 mg. Everybody follow me there? Okay, the logic of that? Okay, and then we talked about universal gravitation. Okay, for multiple choice stuff, you have to obviously understand what affects the force of gravity between 2 objects. Remember, that's a key point too. Okay, that force of attraction is mutual. The Earth is just as attracted to the apple as the apple is to the Earth. There's a mutual attractive force between them. Okay, and that is based on the mass of the 2 objects and their separation distance squared. Okay? If I was going to give you a universal gravitation question, okay, it would probably be a net force one. Okay, a 3-body problem. We've done a bunch of those already. Okay, so you know what to do with those. You're calculating all the gravitational forces and then doing a net force calculation after that. Okay, so there's the 3-body diagram. Okay, here's that formula. Okay, obviously mass 1 and mass 2 and the radius squared, and that force of gravity is mutual. Those are definitely the key points to Newton's universal law of gravitation. Okay, where you'll use that formula most often is in a satellite motion question. Okay, but in a satellite motion question, you are setting this formula here equal to centripetal force. Okay, it is this gravitational force that causes something to orbit something else. Okay, so, oh, sorry, I got more stuff on net gravitational force there. Okay, there's like sun, earth, moon, that kind of question. Okay, and then satellite motion. Okay, obviously Fc equals Fg. That's kind of where you start all satellite motion. Remember that those are the key words that indicate that a trick is being played on you. Okay, if you see height, altitude, or above the surface, okay, it's not giving you or not asking for the total R. Okay, and that you may have to do a substitution, okay, if I were to set up the problem in the right way. which I totally would. Okay, other thing to remember about satellite motion is that the mass of the satellite does not affect, okay, its orbital speed or its orbital period. Okay, it cancels mathematically when you start doing anything. Okay, and that could easily be something that could end up as a multiple choice kind of question. Okay, and then the last thing we talked about was gravitational field strength. Okay, sorry, that's just showing that substitution. We've done that a bunch of times. Okay, so gravitational field strength. Remember, there's just one formula that governs how that works. Okay, the big trick there, okay, is obviously to know when it's asking or giving gravitational field strength, acceleration due to gravity. Okay, gravitational acceleration, gravitational field strength. That's all little g. Okay, and then obviously we talked about Kepler. You don't have to do any calculations with Kepler's law of periods, which is what I'm showing you there. Okay, but you do need to know his three laws. Okay, Kepler's the one who figured out that everything in our solar system actually orbits the sun. Okay, he had his law of elliptical orbits, the law of equal areas, and the law of periods. Okay, so just make sure you know his laws, so that if I gave you a multiple choice question or a numerical response question, you'd be able to pick out the ones that are Kepler's versus the ones that are Newton's or Faraday's or whoever. That's it. It's a short unit. Okay, there's not a lot of material in here, okay, which is good for you. That means you can study the limited amount of material very well, okay? Make no mistake, guys, this exam, if you are well prepared for it, is an opportunity to significantly change the exam portion of your grade. Okay? Typically, this is the one people do best on. I'm not going to say it's the easiest. Okay? I'm not saying that at all. Okay? You have to be well prepared for it. But if you are, you can expect to do pretty well. Okay? All right. On the exam, there are 15 multiple choice questions. There are 3 numerical response questions. And there are 5 written response questions. Okay, the written is out of 23. And the whole test is out of 41. Okay, so given that there are 5 written response questions, okay, kind kind of take a look at the major concepts here, and it's pretty easy to figure out what the numerical response and the written response are going to be about. Okay? There's basically going to be at least one question for every major concept, because there are 8 kind of major questions, numerical and written. Right? So expect a gravitational field strength 1, a vertical circle 1, a universal gravitation 1, a satellite 1, okay, an unbanked, a banked, okay, there's going to be one for each. Right? And then the multiple choice will simply be checking your understanding of the concepts. All right, anything you'd like to go over in more detail? Do another example of. Okay, there's a bank curve. If you want to try a bank curve question, okay, if you don't want to do this question, okay, I posted the unit exam review package earlier this week. You can, work on that, okay, or try some stuff from your workbook. Totally up to you.
What's the horizontal rule again?
Tomorrow is just vertical circular motion. So on this one here, they give us theta. Okay, sorry, theta is 16 degrees. Okay, obviously we know G is 9.81. We're looking, and they also give us the radius, okay, 70 meters. We are looking for V. Since it's a bank curve, we just put in the bank curve formula, okay, and isolate V. So we multiply both sides by R times G, and then square root. Okay, so 70 times 9.81. times the tan of 16. Okay, so 14 meters per second. Okay, would be the speed that you could take that banked curve at if it was frictionless, which we can assume bank curves are, unless we're told otherwise. Okay. Any questions on that one? Okay. Give that one a try. Satellite question. Okay. Anybody one more time on this one? Yes? No? Okay. So it says it's orbiting at an altitude of 2 Earth radii. So how far is it from the center? 3 Earth radii. If it's 2 Earth radii from the surface, it's 3 Earth radii from the center, right? Basically what we're looking at is, here's what they told us. The satellite's out here. This is 2R. Well, there's one more R, okay, in there. Okay, so we're looking at R being 3 times 6.37 times 10 to the 6. Okay, and a question could easily be worded that way. You have the Earth's radius on your formula sheet. Okay, so we'll calculate that first because we'll need it. Whoop, 6.37. All right, so we're looking, there's our actual orbital radius, 1.911 times 10 to the 7. Okay, now we want to find the period. So FC equals FG, okay, mv squared over r equals big G times the mass of the Earth times the mass of the satellite, okay, over r squared. And mass of the satellite is going to cancel. I'm going to get rid of, okay, the v squared. Okay, I'm going to get rid of the v squared and the m there because it's gone. And I'm going to plug in 4, come on. Okay, 4 pi squared times r over t, sorry, times r squared over t squared. Okay, that r is going to cancel. This one's going to go away. Okay, and then we're going to solve for period. Right, so we're going to bring period over here. Okay, we're going to bring the r squared here, and we're going to divide both sides by big G times the mass of the Earth, and then we're going to square root that to get the period. Okay, so 4 pi squared times 1.911 times 10 to the 7 cubed, okay, divided by 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Okay, all right, so so the orbital period there is going to be 2.6, we can have as many significant digits as we want, okay, on this one, because we didn't use anything that wasn't already given to us as an absolute on our formula sheet. Okay, that 3, that's a coefficient, not a measured value, okay, so it wouldn't count. But it wouldn't be wrong to have one significant digit either if you really wanted to. All right, so we'd be looking at 26,282 seconds effectively. Okay, remember that when you do this, you are calculating the period in seconds because you've got kilogram meters per second squared equals kilogram meters per second squared. It's newtons equals newtons on a question like this. Okay? Oh, what mode does your calculator need to be in for this test? Yeah, it's always degree for physics. Okay, if you're taking math right now and you can consistently go back to radians, really double check that you've converted back to degree before you do anything for physics. Okay, I did notice, I think there were 1 or 2 people who may have had their calculator in radian mode, okay, on the assignment there as I was looking at it. Okay. All right, what kind of question is this one? Okay, well, I'll let you try it.